Today's lesson deals with looking at how crude oil is refined into products that we can use in our daily lives. Our first ones are going to look at physical processes, and the first one I want to discuss with you is called fractional distillation. So when crude oil is pumped out of the ground, it's actually made up of thousands of molecules that have many different sizes and shapes. And so what happens is they heat them up without oxygen, and that's very important because if there's oxygen present, it'll just combust. And what happens is they send it up what's called a fractionation tower. And you see an example of one here. So this is a fractionation tower. And what happens here is you've got crude oil that's heated that comes in, and it's brought in a gas state. So what happens is that as this crude oil is fed into the tower, it kind of separates out the different hydrocarbons according to their boiling point. And so you know that boiling point and size are related. And so that's basically what happens here. So what happens is as you move up the tower, it gets cooled. Okay, so the temperature is lower. And so as these crude oil particles move up the tower, they actually cool down and condense into liquid, and then they're drawn off at different heights in the tower until you're left at the very top where you've just got gases. So that's the very first process, the process of fractional distillation, and it just uses boiling point as a means of separating out hydrocarbons of different lengths. So I'm going to turn to the next page that you have, and here I have a fractional distillation tower. And what I've got here is basically a mixture of 4 different types of hydrocarbons. Okay, so A, B, C, and D. The A's are the lightest, so they're gases and light gasolines. B is diesel, kerosene, and other types of gasolines. Again, remember, these are all mixed up. C are light and heavy gas oils. So think about the things that go into your car, the oil in your car. And then D are things like greases, waxes, and tar. So tar being used for example, paving. So what happens is, as I said before, you can see that as I go up the tower, the temperature decreases. The temperature basically goes down. And remember that the longer the hydrocarbon chain, the higher the boiling point. So the higher the temperature you've got to reach before it boils. And so as you cool it down, the ones that took the most energy to boil are the ones that are going to condense back down the soonest and the fastest. So the other thing here that you will see is that they make it through, so the gases make it through these little, basically what are called bubble caps. And so these are found, these are trays, different tray levels. And so the gases are forced through the liquid hydrocarbon at that temperature, and it also helps with the condensation and helping to trap the gases. So here we go. We've got a mixture of crude oil made up of A, B, C, and D. It goes into the fractionation tower. And what happens is right away, you get the very long hydrocarbons condensing and being drawn off the fractionation tower. So basically, it's going to be these guys here. Then the rest, so D is gone, the rest, A, B, and C, continue to move up the tower until, again, they condense out. And so then they are drawn out. And again, the next longest ones are going to be drawn out. And then again, this continues moving up the tower, okay, until B, which are the like gasolines, are drawn off. And then basically you collect substances that are usually gases with really low boiling points. So that's the idea of fractionation tower. And the key thing to remember is that the longer hydrocarbons are going to condense out at lower places on the fractionation tower than the shorter ones because they have higher boiling points. So when you cool them down, they will condense out faster. So I do have a short little animation to show you about that. And it's basically here. And these look like little snakes, but it actually illustrates what's going on relatively well. So you can see here that we're heating up crude oil, and you can see that depending on the length of the hydrocarbon, or the little snakes here, is where they condense off. So you can see that the shorter ones travel up really high up through the fractionation tower, and the longer ones actually settle out much lower. So that way you're able to separate the different components of crude oil into different fractions that have, similar boiling points. So there's still a mixture of them there, but what ends up happening is that they are, have relatively more similar characteristics than they had with the mixture of crude oil. All right, so that is the first thing that's usually done with crude oil as it's pulled off or pulled out of the ground and it's processed into a more usable form. But even then, that doesn't give enough of the fractions that we use for transportation. So gasolines, jet fuels, diesel, all that kind of stuff. We use a lot of that for fuels to move things around, and fractional distillation doesn't give us enough of that. So there's a few other things that we can do to the different fractions that we've separated out. The second physical process, and it's a physical process, not a chemical one, is called solvent extraction. And with solvent extraction, what happens is you use the characteristics of like dissolves like to pull things out of solution. So for example, a lot of times, again, this hydrocarbon that we pull out, this crude oil that we pull out of the ground, isn't pure crude oil. There's other substances dissolved in there. A lot of times things like sulfur. And so with solvent extraction, what we're able to do is use the different solubilities of what we want and impurities, and use it to separate out the stuff that we want away from the stuff that we don't want. All right, so it's important for you to remember that there are two physical processes: fractional distillation and solvent extraction. Now, after, again, we get these fractions of hydrocarbons, there are some chemical processes that we do to, again, increase the type and quality of hydrocarbons that we use for fuels. And these are the beginning of the chemical reactions that you need to know for organic chemistry. So just remember how you needed to know about things like, single replacement, double replacement, formation, decomposition. These are the ones that are involved in organic chemistry that you've got to be aware of. So our first one here is called cracking. And what this does is it literally takes a very long hydrocarbon chain and it breaks it down into shorter ones. So that's basically the idea behind cracking. Now, there are three types, and the only ones that you really need to know are the second two. The first one is an older one, and what it does is it just uses high temperature and pressure to crack long hydrocarbons. And again, it's not really used today. Catalytic cracking uses a catalyst. And if you remember from thermochemistry, catalyst will sometimes reduce the temperature needed in chemical reactions to help speed things along. And so you end up having a safer reaction and also better results. So here are a couple of examples. And remember, these are balanced equations. So the number and type of atoms should match before and after the arrows. So here I have a very long hydrocarbon, 17 carbons long. And it basically gets cracked into smaller chains. So one that's 9 carbons long, the other one that is 7 carbons long. Now, sometimes this produces a little bit of carbon left over, because remember that if I'm going to be breaking a carbon-carbon bond right here, and I break it, then these carbons are going to need, right, something bonded to them, right? Because carbons need to have 4 bonds around them. And so one way around this is to kick out a carbon. And this is basically soot, that black, okay, fine powder that you get. All right, that's kicked out. Sometimes you do produce less soot, and what happens is that you get something. So if you take a look at this one is all single bonds because this is CN, H2N plus 2. But this one here, it's CN, H2N. So basically what I've done here is created something with a double bond. And that deals with the problem of breaking longer chains into shorter ones. But whichever way that it happens, and by the way, when you do this cracking, you can't control the shape or the length of these chains. So I've written one that's 9, one that's 7, but I can have like one that's 10 and one that's 7, one that is, one that's, 5 and the other one that's 12. Okay, so this just cracks them into smaller ones, but there isn't a way of predicting the size and the length of what these are going to break down into shorter chains into. All right. Now, again, although this is useful, because of this soot, it's not often used anymore. Now what's done is what's called hydrocracking. And what hydrocracking does is it adds a little bit of hydrogen. And what it does is it provides that, that place, okay, that bond, but with the hydrogen to kind of make sure that every carbon has 4 bonds attached to it. So you can see it here in this equation. I have 17 carbons, so 9 and 8 is 17 carbons, 36, 37, 38 hydrogens, 20 and 18 is 38, and no soot. Okay, so that's usually why hydrocracking is preferred to catalytic cracking, although it is still done. So how do you recognize that you have a cracking reaction? And the way to think about it is that you're starting with a long chain and you're producing 2, sometimes more, but for the purposes of Chem 30, we tend to limit ourselves to 2 shorter chains. And these shorter chains are then able to be used as fuels. So C17 would be too thick and would gum up an engine. Something with 9 carbons and 7 carbons will very readily burn in an engine. All right, so the last thing I want to do is, for whatever reason, to help me remember cracking, I think about spaghetti and cracking it into 2. And I don't know where that came from in my mind, but that's what I think when I think of cracking. So taking a long string and then breaking it up into 2 smaller ones. All right. So that's the first kind of chemical reaction that you need to recognize in organic chemistry, where you take a long hydrocarbon and you break it up into smaller ones. If you add hydrogen to it, then you don't produce any loose carbon that can result in some soot. All right, so that's the first thing. The second thing here is, the second type of reaction is called reforming. And what reforming does is it takes really short molecules that are not 100% usable in gasoline, and then it converts them into aromatic ones. And remember, aromatic molecules are ones that have the benzene ring. Okay? And these burn better. They actually make the burning process a little smoother in your car. So here you can see that I have 5, 6, 7, so heptane. And what I've done is I've changed it. And again, this is through the process of using catalysts. This changes it to basically methyl benzene. Now, if you recall, benzene, the formula for benzene is C6H6. So what happens here is you produce a whole bunch of hydrogen gas as a result, because forming that benzene ring releases a lot of hydrogen. And so very quickly, if you take a look at the formula here, benzene is C6H6. Because I have one methyl group here, this is going to be C6H5CH3. So that's the formula of methyl benzene. And so if we count our carbons, we have 5, 6, 7. Okay, so C7. Our hydrogens are 6 for the two groups at the end. That's 10. So C7H16. Here then, I've got C7, so 6 from the benzene ring, 1 from the methyl group. And then here I've got 5, 6, 7, 8. So I need another 8 hydrogens, right, in order for this to balance. And that's where my 4H2 comes from, all right? So again, this is kind of the second one you need to be able to recognize. It's called reforming. And what you have is you have a straight chain that forms a benzene ring. And it can have 1 branch, 2 branches, 3 branches, doesn't matter, but it forms a benzene ring and a whole bunch of hydrogen gas. All right? And the last one with crude oil refining is called alkylation or isomerization, but we tend to call it alkylation. And again, what this does is it increases the quality of gasoline by increasing the branches in the molecule. So by having branches, you actually get better burning in an engine. So again, same formula, C7H16 here. Okay, and you can see that this is exactly the same. So 1, 2, 3, 4, 5, 6, 7. And if you count the hydrogens, you will see that it's 16 as well. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So these are isomers of each other. All right. So again, the name for this one, heptane. And this is going to be 2,4-dimethyl pentane. So slightly different properties, and 2,4-dimethyl pentane burns better in a car engine. All right, so for today then, that's the lesson for today. What you need to know about crude oil refining is that there are some processes that just use physical properties of hydrocarbons. The first one uses boiling point, and it sends vaporized hydrocarbons up what's called a fractionation tower, where as you go up, it's cooler and you condense out, so turn back into a liquid, different fractions of hydrocarbons. The second one uses the physical property of solubility. And this is really important for getting rid of impurities. So by being able to differentially dissolve the impurities, let's say, in a particular solvent, you can remove them from the rest of the hydrocarbons. After that, we're down to chemical processes where we've got chemical reactions. And the 3 kinds that you need to be aware of are cracking, reforming, and alkylation. Unlike the chemical reactions that we learned in inorganic chemistry, predicting the products is a little bit more loose, because what happens is you can get a lot of different kinds of products. So the idea is to look at the big picture. In cracking, you're taking a long molecule and making 2 or more shorter ones. The one that you need to be aware of is hydrocracking, where you add a little bit of hydrogen and prevent some soot, which is just carbon, forming as an impurity. The second one is reforming, where you're taking a long chain and you're making it into a benzene ring, a molecule that contains a benzene ring. So that's called reforming. And the last one is alkylation. And remember that whenever you name branches, they have the YL ending, which is why alkylation has the YL in it as well. And there you're taking long branches or long chains of hydrocarbons and you're changing them so they have branches instead. And again, this process increases the quality of the fuel. Now, we're not talking about how this is done at all. That's complicated and beyond the scope of our course, but you do need to be able to recognize these three types of chemical reactions in organic compounds.